20th century physics and general relativity and Einstein stuff, as well as in the context of astrophysics and how stars die. The most massive stars do become black holes. So we talked about all of this last time. And then I believe I think it was Reese, I'm going to blame him for everything. And I think he will own the questions that he's been asking. That led to basically me having to think about our own sun. And our sun is basically one of those stars which will eventually become a white dwarf. Reese says guilty. Trish says, hi, I'm sorry, I'm at school. Okay. Now Saad says, long time meet you. I will be right back. Thank you. Yes, of course. I'm still here. Class is still not dismissed. We're very much in the middle and just getting started. So, come and join. Thank you so much. Hi, I'm back. Very nice. Welcome. So basically, after kind of having surveyed all these different ways in which stars can die and become either a white dwarf or a neutron star or a black hole, I realized, you know what? Our sun, obviously very young, obviously still on the main sequence, obviously making obviously making helium from hydrogen. Those are basically, there were a bunch of things generally that I do know about our sun, but there's a ton of details that go into where a main sequence star. So first of all, a star has many different phases. We actually touched upon this where a star will spend a very long time on what we call its main sequence. Once a star gets into its giant phase, where it's truly the word is giant, where it will become bigger, puff up, it spends less time in its giant phase. It becomes a more inefficient source of power. And pretty much, in short, a star will die if it runs out of its nuclear power. If it basically, it's done burning whatever it is doing to make whatever else. Like, for example, our sun is currently mainly making helium from hydrogen. So the main nuclear physics it's doing is going from taking hydrogen and turning it into helium. If it were to kind of significantly stop doing that, then it's basically getting closer to its death. So ultimately, stars have two main things, nuclear physics going on, as well as its own big gravitation, because a star has a lot of mass. So it can actually collapse under its own gravity, under its own gravitational forces. Basically, all of the mass can just kind of collapse on itself if it does not have another opposing force, which is in this case, the nuclear power. So when stars run out of their own nuclear power, which keeps them burning, you will basically get the death of a star, and then you will be left with a stellar remnant after there has been some sort of explosion in the form of like a supernova or something like that, where there might have been a core collapse, basically, and ultimately you get the remnant, which is either a white dwarf or a neutron star or a black hole. But really, there are many, many other steps that are sort of in between from where the sun was, or from where the star was kind of developing and going through various phases and evolving and aging and going through different phases to where it will then supernova, core collapse, and turn into a remnant. Lots of different steps. My BFF is going to type here. Hi, Trish. Hello. Welcome to Trish, as well as her BFF and everybody else. Thank you so much for joining. Thank you for being in the live. Thank you for liking the live. Thank you so much. So there are really, really quite a lot of details. And we even looked at a star that is sort of the size of our own sun versus a star that is more like a 5 solar mass type of star. So depending on the mass, so another thing we looked at also is that the mass of the star heavily determines what will be the fate of that star, how it's going to die, how it's going to evolve, how it's going to eventually die, and what type of remnant it will make, which of course are white dwarfs for the lower mass stars, neutron stars for the heavier mass stars, and black holes for the heaviest massive stars. Hi, Brilliant. So basically, that's kind of where we were at. So in order to understand more about our own solar system, because we do have a sun and a star, the star in our own solar system is, of course, our sun, just the one. We just have the one sun. So it is rather special to us. In general, I am not a super duper expert on our own solar system, on our own planet, or even our neighboring planets, or our own star, which is the sun. But in this case, I felt, you know what, I should learn a little bit more. So that's what we're going to cover tonight. And basically, for this, we're going to reference this book. Hi, Harper. Called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. We have used this book a lot, and I found a very nice chapter on the solar system in this book, so we can talk about this using this book. So here are some basic facts about our own solar system. The sun contains 99.8% of the mass in the solar system. So if you were wondering, as you know that there are, at this point there are 8 planets in our solar system. There's some asteroids, there's some things, but there's some planets. We're on a planet called Earth. We have a bunch of other planets too in the solar system. We used to say that there were 9 planets. Now there's actually 8 because one of them is a dwarf planet. There's some other dwarf planets as well. But the sun, which is the star in this solar system, contains 99.8% of the mass in the solar system. So everybody else is really quite much smaller. What is your favorite planet? I think that is safe to say that my favorite planet is just Earth. The Earth is my favorite. What is your favorite planet? So most of the remaining 0.2% of the mass is confined to a flattened disk. So things get very interesting when we look at things in a little bit more specifics or details. You didn't care about the Earth the other night. Well, I didn't care that the Earth is going to probably go away at some point. Or you asked about the fate of the Earth and the fate of the sun and, the stars die and all that stuff. But in other contexts, I like the Earth. So most of the remaining 0.2% of the mass is confined to a flattened disk. Within this disk, all the planets revolve in the same direction. Most, but not all of the planets rotate in the same direction, and all objects have similar ages, which is 4.6 billion years when measurable. You tell her, Doro. Fight, fight, fight. Yes. So, did you know that all the planets revolve in the same direction? Most, but not all, of the planets rotate in the same direction, and all objects have similar ages, which is around 4.6 billion years when measurable. Ah, she rocks. Just had to say thank you. So we have a plot here. I might show it at some point. We have Mars, Venus, Earth, Mars, all of that in this plot with the mass going in the y-axis and astronomical units or a distance measure in the x-axis. The 8 largest objects orbiting the sun have been given the collective name planets. The rocky and metallic objects in the asteroid belt lying primarily between the planets Mars and Jupiter. So some of this might be reviewed to you guys, but did you know that the rocky stuff between Mars and Jupiter are called asteroids? The largest asteroid, Ceres, is also a dwarf planet, according to the definition approved by the International Astronomical Union. Wow, there's a union for this. The icy objects beyond the orbit of Neptune are called trans-Neptunian objects, TNOs. Wow. Many of the known TNOs are in a region just beyond Neptune called the Kuiper Belt. Am I saying that right? Kuiper, K-U-I-P-E-R. The largest known TNOs, Eris, Pluto, Haumea, and Makemake, are also dwarf planets. So Pluto is now a dwarf planet. I know we grew up, at least I grew up, considering Pluto as a planet, but now it's a dwarf planet. Drink water. Well, thank you for the reminder. Pronounced Kuiper. Is it Kuiper? We will Google it. I don't know if Maybe it's Kuiper. Okay, thank you. All right. So the planets can be divided into two major types or families, each named after their largest member. The smallest terrestrial planets named after the Earth, alias Terra, terrestrial Terra, are closer to the Sun. The largest Jovian planets named after Jupiter, alias Jovi, are farther from the Sun. Hopefully we kind of knew that. The characteristics, so the thing with what I've realized about the planets in our solar system and just in our solar system is that there are a lot of things that are obvious because we learned it in school, like when we were young, but then there are things that are not as obvious. So I can get tripped up. So we'll see what we learn here today that we didn't know already. It'll be an interesting discussion, and you can always comment too if you know something that we're not covering yet already, or if something is new to you or old to you. The characteristics of the two families are compared and contrasted in a table over here where we see the mass, composition, rotation, satellites, and distance from Sun. So I'll summarize that for you in a bit. Any useful theory for the origin of the solar system must explain the observed differences between terrestrial and Jovian planets. In addition, the following questions should be addressed. Why are planetary orbits nearly circular? So we know that they're elliptical, but why are they, nearly circular? What is the nature and origin of the small debris, such as comets and asteroids? What is the origin of the planetary satellites, such as the moons? Why are there differences in chemical composition among bodies in the solar system? Wow, like pomme de terre, apple of the earth. Oh, really? Potatoes are apple? Oh, yeah, potatoes are apple of the earth. Wow. Pomme de terre, apple of the earth. I didn't know that. Thank you so much. Reese, continue to share more knowledge with us. Thank you. It's French. The dwarf planets Ceres, Pluto, Makemake, Haumea, and Eris don't fit into the scheme. Ceres resembles the rocky satellites of the solar system, while Pluto resembles the icy satellites. The properties of Makemake, Haumea, and Aries are as yet poorly known, but their high albedo or reflectivity indicates that they have icy surfaces. Bye, Harper. Tuna is chicken of the sea, and alligators are swamp puppies. Oh, goodness. So basically, when we consider stars, often we say their masses in terms of our solar mass, our sun's mass, right? When we say one solar mass, it's one sun mass. In terms of planets, we often Hi, Stephen. Hi, Stephen, you're back. Yay. We often compare to the Earth mass, so one Earth mass, right? So terrestrial planets, that is the ones that are the ones that are smaller, basically, have low mass. They're less than the mass of the Earth. Jovian planets are greater than 10 Earth masses. Composition of the terrestrial planets are rocky or metallic. Composition of the Jovian planets are gaseous or icy. The rotation of terrestrial planets is considered slow, where the period is greater than or equal to 24 hours. So our 24 hours, it's even, might be, the rotation is slower for the other terrestrial planets. For Jovian, it is fast. The period is less than 18 hours. Satellites, terrestrial planets have a few. Satellites of Jovian planets, they have many. Distance from the sun is less than 2 astronomical units for the terrestrial planets and greater than 5 astronomical units for the Jovian planets. Steven says, I'm watching you on my TV and chatting tonight. Oh, nice. Thank you so much. Thank you for watching me on your TV. Why are there rings around the Jovian planets and not around the terrestrial planets? So that's another question. So this is what I meant. When I was reviewing this, I was like, you know what? There are things that people, kids are taught about the solar system, about our planets, about about our neighboring surroundings, basically, in this galaxy. But there's always more details that are left out in school and we might not know. For example, why are there rings around the Jovian planets and not around the terrestrial planets? Why are the terrestrial planets chemically differentiated with a rocky outer layer wrapped around a metallic core? We will first describe the physical characteristics of the constituents of the solar system, introducing new physical concepts as necessary. We will then try to put these elements into a single coherent picture of the solar system. Yay! So that's what we're gonna do. My favorite planet will always be Pluto, and Saturn was so happy when New Horizon visited Pluto. So you mean the dwarf planet Pluto and the regular planet Saturn. What is your, I'll ask, what is your favorite planet? Pin message. Pluto will always be a planet. Yeah. You know, some people are willing to die on the Pluto as a dwarf planet hill. And what can I say? At this point, it's whatever for me. I really don't care enough about planets in general to, you know, that. But yeah, my favorite planet, just to keep it simple, is Earth. This is an anti-Earth stream. Oh, come on. Pluto gang, there you go. The masses of astronomical objects are measured by looking at how they accelerate neighboring objects. It is particularly easy to measure the mass of a planet when it has a nearby small satellite. In that case, it is a simple matter of applying Kepler's third law. So that's so interesting. If somebody has a moon, yeah, me too. I mean, I grew up with Pluto being a planet. I get it. So basically, planets that, if you have a moon and if you see sort of its behavior with Kepler's third law, you can actually figure out the mass of the planet. Isn't that cool? Isn't that so nice? That math and physics helps you to determine things with classical, this is classical physics. So amazing. There you go. Planets that do not have satellites, that is Mercury and Venus, pose a more difficult problem. So basically, if somebody has a moon, such as a planet with a moon or many moons, looking at the moons, we can basically figure out the mass of that planet by doing Kepler's third law. I want a cup of tea, but I'm ill. Carry me someone. Oh no. Hopefully you can make this cup of tea or somebody can help you. Gonna drag myself down. I do love our home world, but I will admit I love Io and Titan as moons. Yeah, that's okay. Actually, next I'm gonna ask you about moons. What is your favorite moon? So, so there are some things about that. Now, before the advent of interplanetary space probes, the masses of Venus and Mercury were determined from their tiny perturbations to the orbits of other planets. Wow. Much more accurate masses are now available from space probes that have flown by them or orbited them. The radius r of a planet is computed from its measured angular radius and its distance. The mean density can then be computed from the known radius and mass, which is rho is equal to 3m over 4 pi r cubed. Densities of rho getting around 700, which is 2,000 kilometers per meter cubed, are typical of Jovian planets, indicating a composition that is mostly gas or ice, where ice in the language of astronomers can refer to frozen water, but also to frozen carbon dioxide or dry ice, frozen methane, and frozen ammonia. So what we mean by this mostly gas or ice Jovian planets is the ice can be frozen water, frozen carbon dioxide, frozen methane, frozen ammonia. The lowest density Jovian planet, Saturn, has a mean density of 710 kilograms per meter cubed, which is less than that of water. Densities of rho going from 3,000 to 5,500 kilograms per meter cubed are typical of terrestrial planets, indicating a composition that is mostly rock and metal. Look at that. From all these densities, they know. I grew up with the Apollo moon landings. Oh, wow. Look at that. From these densities, they can figure out the composition. The surface temperature T of objects in the solar system depends on a number of factors. Since the sun is an important source of energy, the temperature of an object depends on its distance from the sun and on its albedo or reflectivity. However, the surface temperature also depends on whether the object has any internal heat sources and whether it has an atmosphere that can act as an insulating blanket wrapped around its surface. So many things. The sun, to a rough approximation, radiates like a black body, so we can do math with the sun's luminosity. Ooh. So they have done some math of the equilibrium black body temperature for a spherical black body of uniform temperature at a distance r from the sun. Earth and our moon. I grew up with the Apollo moon landings, Earth and our moon. I'm dubious about the moon landings. If I can put my... What? Hi, God is the best, so is family. Reese, are you saying that we did not land on the moon? So, basically, there's some... You know what? We're going to read about this. So there's some mathematics I don't think we did. Are you serious? Why? Why do you think we did not land on the moon? So, okay, so after the black body math, we'll keep going. For purposes, okay. The Earth and Neptune are rapid rotators, and although Venus is a slow rotator, it has a dense atmosphere with global mixing. We see, however, that all the planets are warmer than expected. Neptune is warmer than expected because, like all the Jovian planets, it started its existence much hotter than it is today and has not had time to radiate away all its internal heat. Both the Earth and Venus are warmer than expected because of the greenhouse effect. So this greenhouse effect, because of having an atmosphere, can make the planet warmer. Ooh, so look at this. Venus has... Oh, look at that. Venus has a temperature of... What is TBB? T black body. Got it. TSS, subsolar black body temperature. I will admit, I do believe we landed on the moon. Me too. I believe we did land on the moon. Anyway, moving on. The greenhouse effect occurs when a planet's atmosphere is transparent at visible wavelengths but opaque at infrared wavelengths. Oh my gosh. This is so cool. We're going to learn about greenhouse effects. So because we have an atmosphere, listen up. The greenhouse effect occurs when a planet's atmosphere is transparent at visible wavelengths, but opaque at infrared wavelengths. To see why that influences temperature at the planet's surface, consider the energy radiated by the warm surface. For the Earth, with Tp around 290 Kelvin, the Planck spectrum peaks at lambda p wavelength of around 10 microns. For Venus, with Tp around 740 kelvins, so a lot higher than Earth, the peak is 4 microns. These wavelengths are in the infrared range of the spectrum. If the atmosphere is opaque at infrared wavelengths, the radiated light will not freely escape from the atmosphere. Instead, it will be absorbed and re-radiated until the light energy makes its way to the upper atmosphere. Isn't that cool? Where the optical depth at infrared wavelengths drops to around tau of 1. Then, at last, the light can escape. Thus, the photosphere of the Earth and Venus, the layer from which their radiated infrared light escapes, is higher than and cooler than the solid surface of the planet. Naturally occurring greenhouse gases, including water vapor, H2O, carbon dioxide, CO2, and methane, CH4. The greenhouse effect is particularly strong on Venus because its dense atmosphere is roughly 95% carbon dioxide. Oh my gosh. The flux of light we observe from a planet depends on wavelength. Consider as an example the planet Neptune. With a measured temperature of T of 59 kelvins, so that's very low, using Wien's law, its spectrum should peak at a wavelength of around 50 microns. In the far infrared, the light we see from Neptune at visible wavelengths is reflected sunlight modified by absorption in the atmosphere of Neptune. Uranus and Neptune both appear bluer than the sun at visible wavelengths because their atmospheres contain methane, which strongly absorbs red wavelengths of light. The spectrum of a planet can thus be roughly approximated as the sum of two blackbody spectra. One spectrum is that of reflected sunlight, containing both the Fraunhofer absorption lines of sunlight and any absorption lines contributed by the planet itself. The other spectrum is that of planet's thermal emission. The reflected sunlight has an integrated energy proportional to the albedo A, which is reflectivity. The thermal emission has an energy proportional to 1 minus A, plus any internal source of energy. For instance, iron oxide in the soil of Mars strongly absorbs blue light and thus makes Mars appear reddish at visible wavelengths. So Mars does appear reddish, that's true. And there's also a lot of iron oxide in Mars. Mars looks red because it's rusty. Mars is rusty. Rusty Mars. The thermal emission peaks at 13 microns, corresponding to a temperature of around 225 Kelvin, which is around minus 48 degrees Celsius, above average for Mars. So it's kind of cold in Mars. Everybody who wants to go to Mars, it's kind of cold there. Who all believe in the moon landing? Yes. Please write in the chat if you believe in the moon landing or not. I did not think that that was a debate, but sure. An underlying reason for many of the observed differences between terrestrial and Jovian planets is that the Jovian planets have a chemical composition that closely resembles that of the sun. That is, they are mostly, so look at this. An underlying reason for many of the observed differences between terrestrial and Jovian planets is that the Jovian planets have a chemical composition that closely resembles that of the sun. That is, they're mostly hydrogen and helium, which is what the sun is doing. The terrestrial planets are deficient in hydrogen and helium because they're too hot to retain such light elements. Let's consider the conditions under which planets can retain different atmospheric gases. The hotter a planet's atmosphere, the higher the random thermal speeds of the individual gas particles. In a dense atmosphere, though, any individual particle will travel only a short distance before colliding with another particle and changing its velocity. In the Earth's atmosphere at sea level, for instance, we computed the mean free path of a typical molecule to be only around 400 angstroms. Angstrom is 10 to the minus 10 meters, okay? However, at higher levels in the atmosphere, the density of molecules decreases and the mean free path therefore increases. At some height in the atmosphere, the mean free path increases to the point where a gas particle moving upward faster than the escape speed is able to escape from the atmosphere before colliding with another particle. This height is called the exobase, and the layer of the atmosphere above the exobase is called the exosphere. Oh my gosh. So, okay, so now there's some gas math, which basically says that the Earth's exobase has a higher temperature than the atmosphere at sea level because the upper atmosphere is heated by interactions with high-energy solar wind particles during daytime. The exobase temperature is around 1,000 kelvins. Scaling to the temperature of the Earth's exobase, we find that the condition for retaining a gas is, there's some equations for conditions of retaining a gas. That's the Earth where Rx is 1.08 can retain gases. So basically, this is all about can we retain gases or not. That Mercury would be able to retain only highly massive molecules in its atmosphere. So during daytime on Mercury, the retention condition for gas particles is 34, where I think that 34 is the number given to highly massive. Love your streams, but we definitely never landed on the moon. Everyone is coming out to argue the moon landing. Yes, they are arguing the moon landing. Not something that I thought we would be doing. Somehow, Reese, is this you again? You did this, didn't you? Reese is the one who said that he does not believe in the moon landing. And now there are other people too who all believe in the face of Mars. How about Uranus? I'm with Elon Musk. I want to land on Mars. No, we never landed on the moon. We will land on Mars one day, I'd say in the next 10 to 20 years, and we landed on the moon, says Steven. Moon landing deniers are winning. Are you serious right now? What have you done? What have you done, Reese? Okay, so we skipped over some math, but basically there's some math for which molecules will be retained by a planet depending on temperature and gas and all that. We will get to another part now. Formation of the solar system. We will talk about formation of the solar system. Harper, that's okay. Let's forget about the moon landing, but one last thing, we did land on the moon. Done. So now we will give a broad overview of current ideas about how the solar system formed. The modern view of planetary formation is that it is a natural consequence of star formation. Put simply, formation of planets is a way for a collapsing gas cloud to rid itself of angular momentum so that it can shrink to the size of a star. So when there's a collapsing gas cloud, we may just see a star and some planets. So formation of planets is a way for a collapsing gas cloud to rid itself of angular momentum so that it can shrink to the size of a star. Star formation occurs when a large gas cloud collapses under its own gravity. Since this can happen only if the self-gravity exceeds the support provided by gas pressure, star formation occurs only in dense, cold, and by cold we mean T less than equal to 10 kelvins, regions of interstellar gas. So you need a collapsing gas cloud, but remember, gas also has gas pressure. So you can't, gas wants to do the thing where it goes out, right? And kind of disperses, diffuses. We were just talking about how some molecules, depending on their mass, etc., could be, you know, doing things in a gas way or whatever. There's some math for that. Well, let's think about the gas cloud from which we came. Our Earth came, our planets came, and the sun came. So, star formation occurs when a large gas cloud collapses under its own gravity, since this can happen only if the self-gravity exceeds the support provided by gas pressure. Star formation occurs only in dense, cold regions of interstellar gas. If the collapsing gas cloud has a net angular momentum, it will collapse until it forms a rotationally supported disk. The dense central region of the disk ultimately becomes a star, while smaller condensations that occur within the disk ultimately grow into planets. So we are just itty-bitty little condensations of this gas cloud. And the dense central region of the disk of the gas cloud condensation becomes a star, while smaller condensations that occur within the disk ultimately grow into planets. Such rotationally supported dusty gaseous disks called protoplanetary disks are seen around young stars in our galaxy. There's an image of a protoplanetary disk right here, actually. I'll take a look at that. See that thing with the two shiny things and the thing in the middle? Such rotationally supported dusty gaseous disks called protoplanetary disks are seen around young stars in our galaxy. This picture I just showed you shows a protoplanetary disk in the Orion Nebula. The edge-on protoplanetary disk resembles an edge-on hamburger. The dark patty represents a thin, dust-rich disk, and the bright buns, so like the bright parts on the top and bottom, consist of light from the central protostar, scattered by a more diffuse distribution of dust. The first step in planet formation is condensation, the formation of solid particles within the gaseous disk as it cools. Different materials condense into solids at different temperatures. Metals condense at high temperatures. Rocky materials at intermediate temperatures, and ices at low temperatures. So that's the other thing. There is condensation, but depending on the type of stuff that's condensing, I guess, you're going to have condensation. So different materials condense into solids at different temperatures. Metals condense at high temperatures, rocky materials at intermediate temperatures, and ices at low temperatures. Materials that condense into a solid or liquid only at a very low temperature are called volatile materials. The gaseous disk from which the planets ultimately form is hottest at the center, where the proto-sun is located, and becomes cooler with increasing distance. So we were close to that proto-sun, to the baby sun, when the sun was being formed as well from this gas cloud. So because we're close to the baby sun, the gaseous disk from which the planets ultimately form is hottest at the center, where the proto-sun is located, and becomes cooler with increasing distance. In the central parts of the protoplanetary disk, only the most refractory materials can condense to form solid particles. A refractory material is one that condenses into a solid or liquid at relatively high temperatures. In the outer parts of the disk, by contrast, the temperature is sufficiently low that even volatile materials can condense. Oh, we have a table of different things that can condensate at different temperatures. So we have metal oxides can condensate at 1500 kelvins, for example, in mercury. We have iron, nickel condensating at 1300 kelvins, silicates at 1200 kelvins, iron sulfide at 700 kelvins, for example, in Venus, hydrogen, or sorry, not hydrogen, H2O or water, which can condensate at 200 kelvins, for example, on Earth and Mars, NH3 ammonia at 150 kelvins on the Jovian planets, CH4 methane at 120 kelvins, for example, on Pluto and Eris, and then argon and neon can condensate at 65 kelvins. Wow. Look at this. Look at this. Hi, we did not land on the moon. How are you? Condensation, more specifically, is the process by which solids grow molecule by molecule, as individual molecules or atoms adhere to the solid body. Hi, Stephen. As an example, snowflakes grow by condensation. Eventually, when are we going back to the moon? As in, when are we going to land on the moon again? Condensation. So now we know different materials condensate at different temperatures, all the way from metal oxides condensating at 1500 kelvins in something like mercury, to iron sulfides condensating at 700 kelvins in something like Venus, to water, for example, on Earth and Mars, condensating at something like 200 kelvins. I guess I mean Americans did. Yes, we did land on the moon. Condensation, more specifically, is the process by which solids grow molecule by molecule. So this is now explaining what condensation is. So solids grow molecule by molecule as individual molecules or atoms adhere to the solid body. As an example, snowflakes grow by condensation. So even snowflakes are a type of condensation. Eventually, however, the major mode of growth switches over from condensation to accretion, in which solid condensates come together and are held together by weak electrical forces. For instance, individual snowflakes can accrete together to form a snowball. Did anyone make a snowball during the snows this winter? In the early solar system, the collisions between individual condensates or snowflakes are gentle. Aww, since they are on similar orbits. Objects grow by accretion until they're roughly 1 kilometer across. These intermediate-sized bodies are called planetesimals. Planetesimals, or baby planets. Near the sun, planetesimals are made of the least volatile materials, metal oxides and metals. Farther from the sun, where the temperatures are cooler, the planetesimals are made of a mix of materials with different degrees of volatility. Eventually, planetesimals are drawn toward each other by gravity and merge to form larger bodies. This process is known as coalescence. Coalescence. Since only the least volatile materials can condense close to the sun, the planets built up the coalescence within 1.5 astronomical units of the sun are rich in low volatility elements, such as us on Earth, even though such elements are relatively rare in the universe at large. These metal-rich and silicate-rich bodies close to the sun are the terrestrial planets. Yay! So once again, eventually planetesimals are drawn together drawn toward each other by gravity, and merge to form larger bodies. This process is known as coalescence. Since only the least volatile materials can condense close to the sun, because their condensation temperature is higher, right? The planets built up by the coalescence within 1.5 astronomical units of the sun, as in a close distance to the sun, are rich in low volatility elements, even though such elements are relatively rare in the universe at large. For example, what the Earth is mainly made of is not something that is super abundant in the universe at large. Again, quiz question, what is the most abundant element of the universe? I know we talked about this earlier, so yes, you guys know that. Hydrogen in the universe. Silica on Earth, but yes, hydrogen is the most abundant element in the universe. And we already talked sort of about how the universe formed from start to the present in one of my cosmology lives, but we can certainly do that again. Yes, indeed. We did land on the moon. We do have lots of hydrogen, though, in the universe at large. Yes. So we have talked about the evolution of the universe, the start of the universe and all that stuff, early universe, Big Bang, nucleosynthesis. So actually, Reese, if you are looking at my live streams from a while ago, I think something called Big Bang, nucleosynthesis, and around there, we talked about the universe from start to the current moment. But certainly we will talk about it again. I will sub. I'm clearly needed here. Yes, for sure. Please do subscribe. Thank you. Yeah, no worries. Yeah, okay, thanks. Yes, for sure. And we will definitely talk about the universe more. You know, we will go back to more of a cosmology topic for sure. It's definitely very interesting. We will definitely talk about the evolution of the universe more. Thank you. Like the stream, please, guys. Thank you. So these metal-rich and silicate-rich bodies close to the sun are the terrestrial planets. So remember, being metal-rich and being silicate-rich is pretty rare overall in the universe. For example, in the universe, mostly what we have is hydrogen, which is the number one most abundant element in the universe. It's what the Big Bang pretty much made. And as you can see, later on, stars and stuff are later on story in the universe. And you need stars to make the heavier elements, heavier than helium. And even helium is made, mostly in stars. So basically, this whole being metal rich and silicate rich is kind of special. So we should be thankful we have this on Earth. Earth is very special in that sense. So these metal rich and silicate rich bodies close to the sun are the terrestrial planets. Since materials with low volatility tend to be dense, the terrestrial planets all have high densities. So let me tell you about some of our densities. So Mercury's density is 5,400 kilograms per meter cubed. Venus's density is 4,200 kilograms per meter cubed. Earth is also 4,200 kilograms per meter cubed. And Mars is 3,300 kilograms per meter cubed. So Mars is less dense than Venus and Earth. So I think I mentioned earlier at one point that Venus is a lot like Earth, actually, in size and apparently the density. So if I had to pick another planet to go to, it would be Venus, but unfortunately, I believe its atmosphere is rather poisonous. Stinky. Yes. Okay. So this is where I listed off the uncompressed densities of the terrestrial planets. In other words, this is the density of the planet would have if it were not squeezed to a smaller volume and higher density by its own gravity. So these are the uncompressed densities of terrestrial planets that I listed off, as in when they're not squeezed further under its own gravity, that would be the density. Note that the uncompressed density of the terrestrial planets decreases. So note that it decreases with increasing distance from the sun. Mercury had the highest density and Mars had the lowest. It is interesting, however, that the uncompressed density of the moon, our moon, is only 3350 kilograms per meter cubed, much less than the Earth's uncompressed density, despite the fact that they're at the same distance from the sun. The unexpectedly low density of the moon is a consequence of its unique formation history, which we'll talk about later. In the outer part of the protoplanetary disk containing planetesimals of both high volatility and low volatility materials, larger bodies are able to form. Once these protoplanets reach a mass of around 15 Earth masses, they're massive enough, given the low temperatures in the outer disk, to retain hydrogen and helium. So they're massive enough to retain hydrogen and helium, massive enough given that the temperatures are lower out there. They're massive enough to retain hydrogen and helium. Since hydrogen and helium are the most abundant elements, being able to hang on to them permits the Jovian planets to grow to much larger masses than the terrestrial planets. Protoplanets grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. So they grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. During and immediately following this early phase of coalescence, the interior and surface structure of terrestrial planets are changed by several processes, among them chemical differentiation, cratering, volcanic flooding, and slower processes of surface evolution. Chemical differentiation is the process by which dense elements sink to the center of terrestrial planets. So how cool is this? So by the way, another reason why I don't know much about the Earth is because that's geophysics. And I did not do geophysics. So studying the Earth, etc., that's a whole nother field. We will learn about it a little bit here today, but this is really a much larger field. Okay, so protoplanets grow gradually by the coalescence of planetesimals until they reach the masses of the planets as we know them today. And then there's pretty much after the protoplanets are formed from the coalescence, there's a bunch of interior and surface structure of terrestrial planets. There are a bunch of processes by which the interior and the surface structure of terrestrial planets are changed. And these are chemical differentiation, cratering, volcanic flooding, and slower processes of surface evolution. So chemical differentiation is the process by which dense elements sink to the center of terrestrial planets while the lower density elements float up to the surface. Since planets form by a jumbled coalescence of planetesimals of differing chemical composition, we might expect that planets would show the same jumble at their center as at their surface. However, study of the interiors of terrestrial planets show that they are chemically differentiated. That is, their chemical composition varies with distance from the center. The cores of terrestrial planets are rich in dense elements like iron and nickel, with uncompressed densities of 8,000 to 9,000 kilograms per meter cubed. However, their outer layers are primarily made of silicate rocks. We know that. Our beaches are made of silica, sand, with typical uncompressed densities of around 3,000 kilograms per meter cubed. Differentiation occurs naturally in a fluid body. So we're a fluid body. Wow. The denser material sinks while the lower density material rises to the top. The fact that terrestrial planets are differentiated is an indication that they were once hot enough to be fully molten. So this differentiation happened where the dense stuff actually sank to the center. Wow, the dense stuff actually sank to the center of these terrestrial planets. So everything was molten enough to where the dense stuff was able to sink and the lighter stuff floated up to the top. So we have sandy beaches instead of iron and nickel beaches. So the cores of terrestrial planets are rich in dense elements like iron and nickel with uncompressed densities going from 8,000 to 9,000 kilograms per meter cubed. However, their outer layers are primarily made of silicate rocks with typical uncompressed densities of 3,000 kilograms per meter cubed. Wow. And pretty much the moon is that same density, but its overall density is lower. Okay. Differentiation occurs naturally in a fluid body. The denser material sinks while the lower density material rises to the top. The fact that terrestrial planets are differentiated is an indication that they were once hot enough to be fully molten. In the Earth, the radioactive decay of elements such as uranium, thorium, and potassium 40 releases enough heat to melt iron. The iron, as it sinks toward the Earth's center, converts a gravitational potential energy into heat, leading to an iron catastrophe that is a runaway heating process that does not cease until the interior is highly differentiated. Wow. So basically, the radioactive decay of elements such as uranium, thorium, and potassium 40 releases enough heat to melt iron. Wow. The iron, as it sinks toward the Earth's center, converts gravitational potential energy as it's sinking, because if you're over here, you have a gravitational potential energy of mgh, right? Where h is the height from the Earth's surface. So if you sink, you release gravitational potential energy, convert that into heat, leading to an iron catastrophe that is a runaway heating process that doesn't cease until the interior is highly differentiated. So basically the interior is molten, so the heaviest stuff will sink to the center and the lighter stuff will sink up. So pretty much that process of differentiation is more and more as things are more and more molten, which the Earth's center is very molten. Cratering. So this is another thing, cratering. Cratering begins as the newly formed planets sweep up the remaining planetesimals. Fermi paradox? I know Fermi. Remind me what the Fermi paradox is again. So that was the chemical differentiation process. Yeah, it is called chemical differentiation. So what I just talked about, the iron and nickel going to the center, and the center being molten because of so much heat from the radioactive stuff, etc., and that leading to even more differentiation within the Earth's molten center. That's called chemical differentiation in the Earth, or in other planets too. Cratering. So now we know that the moon has craters, all those imperfections on the moon, right? It's basically him asking the question, where is the alien life in the universe, and questioning the lack of it. So cratering begins as the newly formed planets sweep up the remaining planetesimals. So as this, remember, the coalescent stuff happens, planetesimals form. Basically, you can kind of continue to sweep up the remaining planetesimals as you're coalescing. The process of cratering modifies the outer crust of the terrestrial planets. For instance, cratering has given Mercury its characteristically pock-marked appearance. Cratering was an important process until about 3.3 billion years ago. At that time, the early period of heavy bombardment ended because the planetesimals and other small objects had been largely cleared out of the inner solar system. So apparently, cratering is when you pick up upon, you basically pick up. Hi, James. Hello. Hello. Hi, aliens. So I guess the period of heavy bombardment ended about 3.3 billion years ago. And pretty much at that point, the small objects had been kind of swept up by these coalescing planets. Volcanic flooding of planetary surfaces. So this is another process. Volcanic flooding of planetary surfaces occurred at the same time as cratering. Fracturing a planet's crust by large impacts leads to flooding of the surface by lava welling up from below. So basically, at the same time as cratering, if you fracture a planet's crust, oh, thank you. For the past 30 odd minutes, I've been watching some. Thank you so much for watching. Thank you for being here. Welcome. So, at the same time as cratering, if you fracture a planet's crust by large impacts, then it leads to flooding of the surface by lava welling up from below. This obliterates the old surface features. Craters are paved over by lava, just as old potholes in a road are paved over by a new layer of asphalt. Surface features on a terrestrial planet can also be worn away by slower processes such as erosion by wind and water. Guess what? Name something in America that was very much eroded by wind and water. I will leave that question to Stephen. At the same time, surface features can be built up by other slow processes such as plate tectonics and volcanism. On a geologically active body, such as the Earth, surface features are in a constant state of flux. So Earth is very much a geologically active body. Of course, geophysics people will know more about that. But we do know of certain surface features that are very much made by erosion by wind and water. And quiz question for the populace here. Tell us some examples of what you know about that. And Stephen will cover the main one from North America. The surface of a terrestrial planet can change with time, so can its atmosphere. The primeval atmosphere of a planet is whatever is left behind by the formation process. So that's the initial atmosphere. The atmospheres of terrestrial planets evolve for several reasons. Outgassing from the planet's interior releases gases that were trapped in the interior during the formation process. So, in the beginning, whatever atmosphere we get is whatever atmosphere, it was left behind by the formation process. But over time, even the atmosphere can change due to something like outgassing from the planet's interior releases, gases that were trapped in the interior during the formation process. These planetary, let's see what Stephen has to say about what famous structures do we know that are results from erosion with water and wind in North America, especially. These planetary belches, so the planet can belch, Earth can belch, have a little bit of a belch. These planetary belches occur as part of the differentiation process and continue through ongoing volcanic activity. Yes, that's what I had in mind. I had the canyons in mind. We have some pretty big, pretty breathtaking canyons in North America. I've only been just up. Oh wow, James. Okay. Right. That's right. Um you've pressed the like button. Thank you. Thank you so much. Can we get 20 likes, please? I think I see 19 likes. That would be nice if we got an even 20. The Blue Ridge Mountains, mountain range that predates the Rockies, Grand Canyon. Yes! I basically had in mind the Grand Canyon or even something like the Antelope Canyon. You know what I mean? Like North America has such amazing canyons. Devil's Tower is another good example of erosion too. Thank you, Stephen. What is Devil's Tower? Where is that, Stephen? Glad you're back, James. You had me laughing hard last time. Yeah, James is back. The thong guy, or sorry, did I say that right? I forget. I forget what. James and his clothes. That's right. Biden's face is also great. Reese, you are already in a lot of trouble. If you cause any more chaos today, Mr. Belgium, that's it for you. I'm bringing down the hammer. You know, whoever I make the mod on this channel usually is the one who just, what's the phrase? Flies off the handle. Like they are the ones causing the most chaos in the stream. Seriously, what you think of me wearing my mother's red rose lace with the matching and relaxing? Well, James, you should wear whatever you want. I think at South Dakota, it's the ancient remains of an extinct Really? Stephen, tell me more. So Stephen, by the way, I am learning more and more about the United States. I still have 17 more states to visit. And actually, South Dakota is one of the states that I have left. Doro, well, make me mod next. I'll go wild after a few streams. I will. You both can be mod. You both can be mod. Here, Doro Madness is a mod too. Let's just see now what Doro does. Doro can be mod too. Reese is a mod who has caused a bunch of chaos, and now Doro we will see. I'll go listening. Thank you. Okay, so one way in which our atmosphere can change is actually by the Earth letting out some belches from its belly. So interior releases of the gas that were trapped in the interior during the formation process. So remember, the planet during formation process could have some gas trapped within the belly of the planet, and these planetary belches occur as part of the differentiation process and continue through ongoing volcanic activity, because it's an ongoing differentiation process where the lighter stuff will come up and the heavier stuff will sink. Okay? Chemical interactions between the atmosphere and the surface can alter the atmosphere's composition as well. For instance, the interaction of gaseous carbon dioxide with liquid water removed most of the carbon dioxide from the Earth's atmosphere and dissolved it in the Earth's ocean. James is not trolling. Doro is now a mod as well. We've added Doro as a mod. I'll have to keep my cool. I like the stream. Been here too long. We might be mods, but we love banter. In the movie, you see Devil's Tower at the end of the movie. Oh, which movie? I don't think I... Oh, Close Encounters of the Third Kind. I see. Okay. So yeah, South Dakota is part of my list. The North America, you know, the United States has a ton of very interesting such things that we're talking about right now. Earth features, right? So James is hilarious. Sure, James, you're dead serious. He has changed into his mother's black silk. Very nice. South Dakota is awesome. Travel for work all the time. Cool place. The 2 best alien movies. So, really, is South Dakota awesome? Can you say some more things about South Dakota? I actually am missing that. South Dakota, North Dakota, I think Montana. I've been to Utah. I did Utah, Arizona, Nevada, you know, as part of my Las Vegas visit. And then I did toured, or what do you call, guided tours of all the different canyons and dams and things like that. Also Wyoming I'm missing. Sorry, Wyoming is where Devil's Tower is located. I had to look it up. Okay, good. Good to know. Yeah, I'm missing Wyoming, North Dakota, South Dakota, Montana, Oregon, New Mexico. Yeah, there's like 17 states that I'm missing at this point. I'm trying to cover all the states in the US. Most of the time for work was in Pierre, the capital. Spent most of it downtown. Pierre, okay? But got out a little bit and saw a bunch of suburbs. Very homey feeling to it. It was one of the best alien movies I love to watch. Is that the mashed potato tower, Stephen? Oh, Reese. Okay. Chemical interactions between the atmosphere and the surface can alter the atmosphere's composition. For instance, the interaction of gaseous carbon dioxide with liquid water removed. So the interaction between gaseous carbon dioxide and liquid water removed most of the carbon dioxide from the Earth's atmosphere and dissolved it in the Earth's oceans. The mechanism by which planetary magnetic fields are generated is poorly understood. In general terms, it's their food. In general terms, it is thought to result from dynamo action in the planetary core. Hot, partially ionized matter wells up by convection in planetary interiors and is deflected by the Coriolis effect. Our expectation then is that the larger magnetic fields will be found to be associated with larger bodies, which will have larger liquid cores, and faster rotators, which will have a larger Coriolis effect. In fact, as we will see, the planet Jupiter, which is both the largest and the fastest rotating planet in the solar system, has the strongest magnetic field. So how exactly we have planetary magnetic fields is something that we don't fully understand, but we will continue to look at going forward. But some of the guesses are that it might have to do with the Coriolis effect, because Jupiter, which is both the largest and the fastest rotating planet in the solar system, has the strongest magnetic field, turns out. So interesting things like that. Now, basically we covered, that was the overview of the solar system. Good night, James. Have a good day at work. Black silk, okay. Has anybody seen the pentagon-shaped cloud formation in the North Polar region of Saturn? Okay, so now let's talk about a little bit more about the Earth and the Moon. Next, okay? We will talk a little bit more about the Earth and the Moon. Pretty fascinating, yeah. So, right. So we just saw that the moon's uncompressed density is lower than the Earth's uncompressed density. And so we will look into a little bit about that. And by the way, there was a footnote that we missed earlier. The Earth is the most massive terrestrial planet. By the way, I hope you knew that already, might have known that already. The Earth is the most massive terrestrial planet and has the greatest gravitational compression. The measured mean density of the Earth is around 5,500 kilograms per meter cubed, significantly higher than its uncompressed density of 4,200 kilograms per meter cubed. So if there was no compression due to gravity, Earth would have the same density as Venus, and Mercury has, remember, uncompressed density of 5,400, Venus and Earth 4,200, and Mars is 3,300. And we saw that the moon was around 3,300 as well. And we will see why, because the moon and the Earth are at the same distance away from the sun. And the Earth is the most massive terrestrial planet. And the measured mean density of the Earth, again, is 5,500 kilograms per meter cubed, which is significantly higher than its uncompressed density of 4,200 kilograms per meter cubed. So those are some more facts. And then now we will go over to learning about the Earth and the moon. I think it's kind of fascinating, actually, to talk about the moon, so we will. Yay! Our moon, right? Our sun, our moon, our solar system. Okay. 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 So I actually like the moon more than the Earth, I think. So somebody was saying that I don't care about the Earth. It's true. I mean, I care about it, but there's different levels of caring, right? I think I actually like the moon more. I love the moon. I love looking at the moon. I mean, it's there, you know. I've always had a poetic relationship with the moon. The moon has always been there for me. So yeah, ever since I was a child, I've kind of liked the moon, actually. The lunar maria are seen as darker, smoother regions on the moon's surface. Did you know? Lunar maria. The moon is always cool. Yeah. Okay, so let's read about the moon a little bit. Let me drink some water and then we will. How are you guys? Actually, it's kind of cold. I'm gonna turn off the heat. Hi, Flowey. Hi, Fuji baby. Oh gosh, it's so cold. It's so cold. The Earth's moon. This sweater, by the way, was made by my grandmother. Yay, grandma fashion. The Earth's moon has an average density of rho equal to 3,370 kilograms per meter cubed. There is a theory that the moon was actually two moons. Okay, about the same as the density of the Earth's crust. Because of the moon's small size, it has cooled more rapidly than the Earth, leaving it nearly dead, geologically speaking. Because geologically active, when things are still kind of happening, you have like molten insides. Grandma fashion? Yes, my grandma made this sweater. I think it might have even been my brother's sweater. I inherited a lot of my brother's clothes, and his like boy clothes still kind of fit me, so here we are. So my grandmother probably made sweaters for both me and my brother. But most of them ended up with me because I fit in them. And that's not something you hear from girls often. It's a nice sweater. Right? Isn't it so nice? She made it. And she's not there anymore, so I have her stuff, the sweaters she made by hand. Hi, Baji. Not something you hear from girls. Well, it helps that I look good in almost anything. Look, the back is red and the front is dark. Oh my god! She's rocking a boy sweater and